In this video, we are going to talk about the triple integral, and I feel like the best way to do this is just to show you a bunch of examples. To compare this to the double integral, the domain is usually an area, and then you integrate a surface that's over the area and you get a volume. So for the triple integral, our domain is going to be a three-dimensional volume, and then we have a surface over that three-dimensional volume in the fourth dimension, which I will not draw for you. I'm actually lucky if I can get the domain and 3 dimensions right. So the fourth dimension is going to be a hypervolume. Our first example is to find the formula for the volume of a sphere or of a ball. So we are going to be integrating over the entire volume, and then the function we integrate will be 1, and then that way we will get volume, and hopefully we'll get 4/3 pi. The first thing I do is I take my parameterization of the sphere. That's x squared plus y squared plus z squared is less than or equal to 1. And I write that in terms of z because I often think of z as depending on x and y. I mean, it's symmetric, so you really could have solved in terms of y. But again, I often think of z as being dependent on x and y. So I solve this equation, and I get z is equal to the square root of 1 minus x squared minus y squared. And technically, it's the positive and negative square root. That will give us the whole hemisphere. But what I did is I'm only going to integrate the top half of the hemisphere for the volume, and then multiply my final answer by 2. I know there's an 8 here, and I'll explain where the other factor of 4 came in, but basically you multiply by 2 if you're only doing the top half of the hemisphere. The next thing I will want to do is take a look and see what the cross-section of what x and y look like. So in particular, if I set z equal to 0, then my x and y are related in this way. If z is equal to 0, then x squared plus y squared is less than or equal to 1. So I'm left with this circle, and I can solve in terms of y, so that y is the square root of 1 minus x squared. These two equations are going to help me set up my limits of integration over here. Oh, and also, yes, the circle. I only parameterize the positive half. The other half of the circle should be y is equal to negative minus x squared, 1 minus x squared. However, I don't like working with negative square roots, so I'm just going to take 0 to the positive half and then multiply my result by 2. So far I've multiplied my result by 4. 2 here for only taking the positive, and 2 here for only taking the positive. And now I'm ready to set up my limits of integration. So I can choose my most complicated formula here, dz, and I'm going to integrate. Again, for the entire sphere, I really should integrate from negative square root of 1 minus x squared minus y squared to positive 1 minus x squared plus y squared, but I multiplied by that a factor of 2, so I could just go from 0. So I'm doing the top half of the sphere. So z goes from my z equals 0 to the top of the sphere. And that's what this is here. And you notice that z depends on x and y. My equation here and my limits, I can have x's and y's. I don't have to. I can have just numbers. But I shouldn't have any z's in here. It should only depend on x and y. It should only depend on these two variables. Next, I should set up my limits of integration for y. And y depends on x as a circle. And again, I only do the positive half of the circle, so I need to multiply by 2 out here. And then y goes from, where's y? 0 over to 1 minus x squared, the edge of this circle here. Last, I look at my limits of integration of x. And x technically goes from -1 to 1. If we're only looking at what x does, right, it goes from -1 to 1. But I multiplied by 2, and I just took it going from 0 to 1. So this is my integral. And you notice again, on the inside, my limits of integration can only have variables x and y and constants. I should see no z's in here because that's the first variable. This next variable that I'm going to eliminate will be y's, which means here I can only have x's. And at the very end, I should have only numbers. Every time you integrate, you eliminate one variable. So a quick example, what I mean by you eliminate a variable, so if you have x, a function of x, and you integrate with respect to x, you're going to get your antiderivative, and it's going to be in terms of x, but then you're going to plug in numbers. So after you've integrated with respect to x, you've eliminated x. So often in differential equations, you talk about integrating out a variable, and that is exactly what you're doing. By the time you're done with your integration, that variable is no longer there. So here, after you're done, if this weren't a 1, but let's just say it was a z, after you're done, you're going to be plugging in these limits of integration in for z, and then you will have eliminated z from here. And so again, this function doesn't have to be 1. It can depend on z, but your limits of integration only depend on x and y, so that after you're done plugging in, you get only a function of x and y. And then after you integrate with respect to y, you'll have a function that's dependent on y, x and y, but then you'll plug this in for y, and then you'll have a function only dependent on x. And then you integrate with respect to x, and you have a function dependent on x, but then you plug in numbers, and you'll have no variables. As we go on and do our triple integrals, you can notice this pattern. And just a note, I have my 8, again, because I only integrated the top half with respect to z, so that was a factor of 2. Then I only integrated the positive values of y, so that was another factor of 2, so that's 4. And then I only integrated the positive values of x, so now I have 2 times 4, so that's my 8 out here. Now that I have my limits of integration, I integrate with respect to z, and I get z, and then I have my limits of integration, z to the square root of 1 minus x squared minus y squared, so I plug that in, and then I get this function here and this double integral, and you see I have eliminated z, and I only have x and y's here to integrate. I plug in my limits of integration, and this is what I get here. So now when I need to integrate with respect to y, so I had to look this up in a table of integration, so I'm going to let this be a squared, my 1 minus x squared equals a squared, and then for my formula x squared, y squared is going to be my x squared, and here is my formula I looked up. So using this formula here in blue to integrate, I get my x over 2, so that's y squared over 2. And then I have my square root of a squared minus x squared, so just my square root of 1 minus x squared minus y squared, plus a, again, is my 1 minus x squared over 2, times arcsine of x, which is my y, over a, here, evaluated at 0 and 1, square root of 1 minus x squared. So you can see here I plugged in my values. I have my last integral. Actually, that was my last integral here with respect to x. And so then I go ahead and take the integral. Fortunately, this is a much easier integral. I plug in, and I get 4/3 pi, which is the formula for the volume of a ball. One thing I want to point out, every time you perform an integration, so like when you perform this first integration, your innermost integration, when you're done, you should have one less variable. So in other words, your limits of integration here should only depend on x and y, so that when you're done, you have an integral of some function. Here it's the square root of 1 minus x squared minus y squared, and then you only have x and y left as your integral. Then this next integral should get rid of the x value. So after you integrate here, you only have a function of x, and then you're integrating with respect to x. When you integrate here, you have your x value, then you plug in your numbers. So again, the idea is here, your integrand should only depend on your last two variables. In this case, it's x and y. Then afterwards, your next integrand should only depend on your very last variable, and then your limits of integration here should be numbers. In differential equations, they often talk about integrating out a variable, and it's because every time you integrate, you get rid of one variable. Here you integrate, you get rid of the y variable. You integrate, you get rid of the x variable. And then at the very end, you're plugging in numbers. My next problem is to let W be the region bound by the planes x equals 0, y equals 0, and z equals 2, and the surface z equals x squared plus y squared, where x is greater than 0, y is greater than 0, compute the integral. So first I drew my surface. Fortunately, I remembered what happens in chapter 1. So this is if I used my contours, my level curves, right? When z is equal to 0, then x squared plus y squared is just that point. When z is equal to 1, we have a circle of radius 1. When z is equal to 2, we have a circle, or 4, we have a circle of radius 4. So you can see you're going to get this kind of bowl shape. But we only want the bowl shape in x, y in the first quadrant, and we only want to go from z equals 0 up to z equals 2. And now we're ready to set up our limits of integration. So I thought the easiest thing to do was to start with the z goes from 0 to 2. And then y needs to depend, I need to know how y depends on z. So I kind of look in the x-axis where x is equal to 0, and I see there's this parabola that's drawn. Another way to see this, again, if we're looking in the yz plane, because we really want to focus on how y and z interact. So when x is equal to 0, we can look at this equation and we see that z is equal to y squared, or y is equal to the square root of z. And I also kind of have my drawing here in the yz plane. I have the z is equal to y squared parabola. So if I look at my limits of integration, my region is bound by y equals 0 and the surface. So in other words, y is going to go from 0 up to this curve here, square root of z. And you really could just do this algebraically by setting x equal to 0 and then y is equal to the square root of z. So I have my z going from 0 to 2, my y going from 0 to square root of z, and then my x, I'm just going to use this equation. It's going to go from 0 up to the surface as well. So here's how I set up my integral. And again, always on the outside there are only numbers. On the inside, you can depend on at most, you should see at most one variable, and that would be the last variable that appears here. And on the innermost integral, you should see at most two variables, and that will depend on these two outer variables out here. And just to look at my limits of integration here, then you can see on the inner part, I am going to be getting rid of the x variable, so my limits of integration can only depend on y and z, which it does. And then I'm going to get rid of my y variable, so my limits of integration only depend on z, and then at the very end I get rid of z, so that I'll have just numbers. And from there you can see I integrate, the integration isn't too bad, I plug in, and my final answer is 8 square root of 2 over 15. The next problem is to set up the integral, so you don't actually need to do the integration. Just set up the integral to find the volume of the solid region bound by the hemisphere x squared plus y squared plus z squared equals 4, where z is less than or equal to 0, so it's the bottom half of the sphere, that's the hemisphere. And the paraboloid z equals 4 minus x squared minus y squared. So here I have my drawing, which I'm going to claim again is super helpful. I have my hemisphere down here, so that's my x squared plus y squared plus z squared is equal to 4. And then in the xy plane, that's where z is equal to 0. I don't know if you can tell from my wonderful drawing, but here z is equal to 0. And the xy plane, we have the circle x squared plus y squared equals 4. Next, I looked at the paraboloid, and to get the top of the paraboloid, I plugged in x and y equal to 0, and I got the 4. And then, nicely enough, when z is equal to 0, we have that same circle. So this paraboloid intersects right at z equals 0 and at the ends of the hemisphere. So that's the drawing. And now I'm ready to write out my integral. And because I actually don't have to plug in any numbers, I didn't try to use symmetry to do only the first octant or anything else like that. I actually went from x is equal to -2 to 2. And then y depends on x, and here we have the circle. Y goes from the negative half of the circle, which is square root of 4 minus x squared, and to the positive half of the circle. Now z goes from the hemisphere up to the paraboloid. So here I have the hemisphere up to the paraboloid. And here I also want to mention the x and y, it's not that important. There's a lot of symmetry here, so you really can switch the order of integration of x and y, but I feel like it's really important that the z is the first variable you integrate, because it's very easy to see that x is going from this curve to that curve. And then it's very easy to see your x and y are related with this circle. So it seems very natural that these two are on the outside. It expresses the circle, and that the z is most easily expressed, right, rather than trying to express it in terms of x and y and seeing how z interacts with x and y. It just seems most natural to say, oh, I'm going to go from the bottom curve to the top curve. This next problem is to set up the integral, the triple integral, to find the volume of the ellipsoid x squared over a squared plus y squared over b squared plus c squared over c squared is equal to 1. And here's my drawing of the ellipsoid, which is actually not very good. This is where you could actually tell me that the drawings aren't useful and they really don't help. But, you know, let's not get too carried away here with our critiques. So here I can solve for z. So the surface is equal to c over square root of 1 minus x squared over a squared minus y over b squared. I could look at z equals 0 just so I can isolate how y and x interact. So we have x squared over a squared plus y squared over b squared is equal to 1. So y squared is equal to b squared times 1 minus x squared over a squared. So now I'm ready to set up my limits. I have x between negative a and a, that's my first axis. Y, then I have this here between negative b square root of 1 minus x squared over a squared, and then up to positive b minus 1 minus x squared minus a squared. And again, this part is, you know, the x and y is in the z, xy plane, where z is equal to 0, you basically have this trace of the ellipse. And then last, I have z. So I integrate 1 dz, dy, dx. And again, I have the pattern where the last integral has to be numbers. The middle integral can depend on at most one variable. Remember, a is the axis, so it doesn't really count as like one of these variables. But it's at least, at most one variable, which needs to be this last variable here, x. And then the innermost integral can depend on these two other variables here. Our next example is to find the volume inside the capsule bound by the paraboloids z equals 9 minus x squared minus y squared, so that's kind of an upside down paraboloid because of the 9 minus the paraboloid. And then also z equals 3x cubed plus 3y squared minus 16. And here they actually gave us a figure, which was really nice. But here it's sort of the paraboloid x squared plus y squared would give you sort of this, give you this shape, right? Because the level curves are circles, but now it's negative, so it's going to be upside down, and then it's raised by 9 units. So here is this paraboloid here, and then we have this paraboloid, which is also, so we have circles, they're a little bit bigger, right? But again, it's sort of this paraboloid shape. And we're at minus 16, so we have to shift down 16 units. And this is this other paraboloid. And what you can see is they intersect, and then this blue area, that's the little capsoid we want to look for as far as the volume. So we want to find the base where these two capsoids kind of, or these two paraboloids kind of intersect and meet and fit together. So this base is this circle here that we're looking for. Maybe it's an ellipse. No, I guess it's a circle here. So we set the two equations equal. So our 9 minus x squared minus y squared, along with our 3x squared plus 3y squared minus 16. And we get this circle here, where x squared plus y squared is equal to 5 halves squared. So now we're ready to set our limits of integration. And sort of, as I said before, for a previous example, the x and y, they're symmetric. They form this circle here. So it's very easy to see these as the last outside. These are the outside limits because we know how to do the circle. You know, we have the radius, and then we have the other variable in terms of the other. And then it's very natural for z to go from the bottom of this parabola, or I'm sorry, from the bottom of this circle to the top of this parabola. So all of this really argues for z being the inside integral and x and y being on the outside. So I was looking at your book, and it seems like they want this whole capsule. I thought they just wanted the top part, but they actually want the whole capsule. So that's going to make our limits of integration a little different than what I originally thought, but it's okay. So first, I did only integrate with the first quadrant, and so we're going to multiply by 4, and we're just going to look at x going from 0 to the edge of our circle, which is 5/2. And then here for our y, again, only in the first quadrant, y is going to go from 0 to square root of 5/2 minus x squared using our equation of the circle. And then finally, since we want to go all the way to the bottom, then our z is going to go from this parabola to the top parabola here. This last example, calculate the volume of the solid W sitting in the first octant and bound by the coordinate planes, so bound by the xy plane, the xz plane, and yz planes. And the paraboloid z is equal to x squared plus y squared plus 9. Again, it's that bowl shape that's been shifted up 9 units. And the parabolic cylinder, y is equal to 4 minus x squared. So here's your parabolic cylinder that's kind of underneath, but I only drew a quarter of it. So you want the volume between this that's in the cylinder and the top of it is going to be where it meets this bowl. I can see from here that x goes from 0 to 2. Y then goes from 0 to, because we're only in the first octant, and I don't need to multiply by 8 because it only wants the first octant. Y goes between 0 to the equation 4 minus x squared for the cylinder. And then z goes from 0 all the way up to the bottom of the. That's it for my example. I have one problem for you to try, so you can pause the video, give it a try, and then on the next slide I'll have a solution for you. So here's the solution, and that's it for this video. Thank you for watching.